Variations in air intake, or P1 pressure, require that the fuel flow to the burners is adjusted so that a fixed RPM is maintained for a selected throttle position at all altitudes and airspeeds. This is achieved by the expansion or contraction of a capsule influenced by P1 pressure, which in turn modifies the fuel flow to suit the new conditions. This capsule, known as the barometric pressure capsule, is incorporated in an altitude sensing unit within the fuel control unit. It's necessary to increase the fuel flow to the engine to make it accelerate. However, too rapid an increase of fuel flow into the engine can cause compressor stall and surge. To regulate the fuel flow under conditions of engine acceleration, an acceleration control unit is fitted within the fuel control unit. The acceleration control unit receives information regarding engine intake pressure, P1, and compressor delivery pressure, P3 for a two-spool engine, and uses this information to adjust a fuel metering plunger. The fuel metering plunger effectively acts as a second throttle valve in series with the main throttle, and it regulates the fuel flow to achieve the fastest engine acceleration without causing stall or surge. Exhaust gas temperature is probably the most important parameter in a gas turbine engine. To obtain maximum efficiency, the engine must be run at the highest possible temperature in the turbine without melting the materials from which it's made. To achieve these conditions and yet still allow the engine to be a practical, user-friendly unit, automatic monitoring of the exhaust gas temperature is combined with a top temperature control unit. The top temperature control facility allows the pilot to select full power at any time without risking a meltdown in the turbine assembly. Thermocouple probes are positioned in the gas stream, either within the turbine assembly or close after it. The output of these thermocouples is used to measure the temperature at the rear of the engine. This output is passed both to the cockpit instrumentation and to a temperature control signal amplifier. The electrical output of this amplifier drives the solenoid, which indirectly controls the fuel flow to the engine. The ability of the compressor to withstand internal pressure is limited by the strength of the materials from which its casing is made. If the compressor casing is subjected to pressures greater than its design maximum, it will break, with probably catastrophic consequences. To prevent compressor casing failure, the fuel control unit incorporates a power limiter device. The power limiter receives signals of both intake pressure, P1, and compressor delivery pressure, P3. The ratio of P3 pressure to P1 pressure can be found by combining these signals. A system of capsules and levers controls the fuel flow to the engine so that a maximum pressure ratio is never exceeded, and thus the integrity of the compressor casing is retained. If excessive centrifugal force is to be prevented from destroying the compressor spools, their maximum rotational speeds must be limited. There are basically two methods of achieving this compressor rotational speed limitation. The first method of controlling the rotational speed of a compressor, usually the low-pressure compressor, depends on an electrical signal proportional to the speed of the compressor shaft. A tachogenerator or electronic speed sensor, which is driven by the appropriate shaft, sends signals to an amplifier. If the output of the tachogenerator approaches a predetermined maximum level, the fuel flow will be adjusted to prevent the maximum RPM being exceeded. The second method of controlling the rotational speed of a compressor is normally used to control the speed of rotation of the high-pressure compressor shaft. This high-pressure compressor shaft drives the accessory gearbox, which in turn drives, among other things, the high-pressure fuel pumps. Fitted within the high-pressure fuel pump is a hydromechanical governor. The hydromechanical governor uses hydraulic pressure as its controlling parameter. The hydraulic pressure, which is generated inside the pump by the rotation of the moving parts, is proportional to engine speed. As engine speed, and thus hydraulic pressure, builds, it acts on a diaphragm, Movement of the diaphragm opens valves which bleed off some of the servo piston pressure, which reduces the high-pressure fuel pump cam plate angle. This reduces the high-pressure fuel pump output and attenuates the fuel flow to the burners. The high-pressure fuel cock, sometimes called the high-pressure fuel shutoff valve, controls the flow of fuel between the fuel control unit and the fuel spray nozzles in the combustion chambers. The high-pressure fuel cock is the control normally used for starting or stopping the fuel supply to the engine. The high-pressure fuel supply may be mechanically controlled by a lever on the flight deck, or it can be electrically controlled by an actuator, which is also controlled by a switch on the flight deck. When the engine is shut down, any fuel remaining in the fuel manifold would tend to boil as a result of residual engine heat. Solid deposits resulting from the boiling will clog the fuel lines into the system, which would be detrimental to the operation of the engine. The dual inlet line fuel spray nozzle system can utilize a pressurizing and dump valve to prevent this happening. When the engine is shut down, fuel pressure generated by the opening of the high-pressure fuel cock, which was holding the dump valve closed, is lost. The spring inside the dump valve will now be able to open the valve and allow the contents of the fuel manifold to pass back to the supply line. At the same time, the inlet check valve will close, maintaining fuel inside the unit ready for the next start. When the high-pressure fuel cock is opened, a signal of fuel pressure is sent to the dump valve, which moves over and shuts off the fuel flow back to the supply line. In moving over, the valve also opens the passageway to the primary manifold. Fuel pressure from the fuel control unit will open the inlet check valve and pass through the filter to the primary fuel manifold. At a predetermined engine speed, the fuel pressure from the fuel control unit will build sufficiently to open the pressurizing valve, and fuel will also begin to flow into the main manifold, expanding the fuel spray pattern and assisting in better atomization. Many modern gas turbine engine installations utilize electronic engine control to enable better fuel economy, better reliability, and prolonged engine life. Two types of electronic engine control are currently in use: the supervisory engine control system, the full authority digital engine control system. The supervisory engine control system uses a computer which receives inputs of various engine operating parameters and controls a standard hydromechanical fuel control unit. The fuel control unit responds to the electronic engine control commands and performs the functions necessary for engine operation and protection. The computer will monitor EPA, throttle lever angle, Mach number, engine intake pressure, and temperature, and will maintain a constant thrust regardless of changes in air pressure, temperature, or flight environment. Any fault with the electronic engine control will cause the system to revert to manual control. The Full Authority Digital Engine Control System, commonly called by its initial letters FADEC, receives all the necessary data for engine operation and takes over virtually all of the steady-state and transient control functions, which includes compressor airflow control. The hydromechanical fuel control unit is now redundant, except for the throttle valve and fuel shutoff cock, which reduces the mechanical complexity of the engine fuel system. The FADEC system will monitor all of the normal engine parameters and prevent limitations being exceeded while controlling the engine through all modes of operation, for example starting, idle, acceleration and deceleration, takeoff, climb and cruise. In other words, it controls the engine in response to the throttle lever position or the flight management computer thrust demand. The digital computer which is required to run the system has to be considered an essential component of the engine, just as essential as the compressor or the turbine. This is because a complete failure of the FADEC system would cause the complete loss of the engine thrust. To minimize the chances of a single failure causing the loss of an engine, the FADEC system incorporates two separate identical digital channels. Each channel is able to provide information to enable all engine functions. The FADEC system can be powered from the aircraft electrical system, but in most modern aircraft the system is driven by a separate generator fitted to the accessory gearbox of the related engine. This concludes the lesson on engine fuel systems.